Welcome you all to this first-of-a-kind keynote. My name is Manish Mehta from the US, and I'll be chairing this session. I'll just make a few brief remarks before introducing the speaker. I think a bit of a historical recap might help set the context and the stage for not only today's keynote, but also tomorrow's microsymposium on NMR crystallography. It's safe to say that the idea of studying crystals using magnetic resonance goes quite a ways back, right to the early days of NMR. So the idea is not anything new. Some of the earliest NMR experiments were performed on crystals. About 10 years ago, the field experienced something of a rebirth, and now there's a vibrant community that identifies itself as NMR crystallography. 3 years ago, a group of us approached the IUCR to create a new commission on NMR crystallography and related methods, which was approved at the Montreal Congress. And here we are 3 years on with a keynote and a microsymposium in the field. And that's a good indication of the emergence and the vibrancy of this field. Our speaker today is Professor David Bryce from University of Ottawa. He did his undergraduate work at Queen's University in Ontario, followed by his PhD work at Dalhousie University with Professor Rod Wassiliessen, who is a founding member of our commission. After a postdoc at the NIH in the US, he began his career at University of Ottawa in 2005, where he's now a full professor. He's an active researcher and a leading researcher in the field of NMR crystallography. He and his team have done pioneering work in studies of materials, studies of low-frequency quadrupolar nuclei, and most recently work on halogen bonds. And so it gives me great pleasure to welcome Professor David Bryce to give today's keynote titled Structure and Properties of Materials by Solid-State NMR Observables.
Okay, microphone on. Okay, thank you for that introduction. It's a pleasure to be here. I'm actually not feeling very well today, so I've brought a chair to sit down, but hopefully I'll get through it, and hopefully there's something of interest for you here today. So thank you for the introduction. Overall, research in my group, just to give you an idea of what we do a range of different things from fundamental solid-state NMR studies, materials characterization, some biomolecular NMR, NMR crystallography, which I'll be talking to you about today, some software development. We look at pharmaceuticals, computational work, obviously polymorphism comes into this a lot, and non-covalent interactions such as the halogen bond is another big thing that we're doing at the University of Ottawa. As mentioned in the introduction, I'm here in part because of this IUCR Commission on NMR crystallography and related methods. And as you can see here, the commission was established in 2014. The commission will serve several useful roles for the community that studies the crystalline state using magnetic resonance, as well as for the larger crystallographic community. And essentially, what is NMR crystallography? Well, we all know NMR. There's a whole range of things we can do with NMR. And this kind of general statement at the bottom here kind of puts it into context. The use of the spin degrees of freedom of the magnetic resonance phenomenon to study the crystalline state of matter. So it's really quite a broad definition of how NMR fits into crystallographic studies. I wanted to highlight a couple of recent, articles and editorials and special issues on the topic as well that have led up to this meeting. So I put together an IUCRJ article leading up to this keynote lecture on NMR crystallography. It's just a very brief overview. And I wanted to comment on, what does this term mean, NMR crystallography? Because there's a lot of different uses in the literature and different interpretations. And so I tried to break it down into what I felt were the important categories. So the term NMR crystallography has been employed in the literature to cover a wide array of approaches to structure determination, refinement, or selection. Broadly speaking, these methodologies may be classified into the following categories. So complete de novo structure determination using NMR data. So this type of thing would be seen, for example, with protein solid-state NMR studies, where the complete three-dimensional structure of a protein is determined basically using only empirical NMR data. You can then have structure refinement against NMR data, where you work in concert with diffraction methods or other methods to put everything together to refine a structure. Or you can simply have cross-validation of structural models using NMR data. So you may produce various models by computation, by diffraction, by other methods, and then you use some NMR methods, NMR data that have a different perspective on the structure to cross-validate this structure. So when we say NMR crystallography, this does not always imply necessarily that we're solving a structure per se, as you do with single crystal NMR. But it's kind of a wide, encompasses a wide array of approaches, and oftentimes diffraction and NMR go hand in hand in producing improved structural models. So Francis Tolel and I wrote this editorial for the Actor Chris C special issue on NMR crystallography, and I'll refer you to that. It has more information on kind of what this NMR crystallography topic means. Some advantage obviously to NMR studies is that we can look at both periodic and amorphous compounds, deal with heterogeneity quite easily. Dynamics is a big strength of NMR for characterizing structure at the same time. And this editorial goes on to emphasize some of the things that I just mentioned about kind of the different opinions in the literature on what this term really means and the wide array of approaches that the term encompasses. Before getting into today's talk, I'll just highlight one final article here. This is in Crystal.com, a highlight on the role of solid-state NMR in crystal engineering, and this kind of goes hand in hand with the idea of NMR crystallography. And so here's the definition from Des Raju, that crystal engineering is the understanding of intermolecular interactions in the context of crystal packing and the utilization of such understanding in design of new solids with desired physical and chemical properties. And so from our perspective, we want to be using solid-state NMR to ultimately contribute to the design and construction of new materials with specific properties. So in this talk today, I won't be talking solely about NMR crystallography, but my title is a little more general on structure and properties of materials that we can get from solid-state NMR. So what I want to talk to you about today is a little bit of background on solid-state NMR in general, and how it's a valuable and sensitive probe of structure, symmetry, dynamics, and polymorphism. I'll briefly run through some of the key interactions in NMR that we use to tease out structural and dynamic information. All of our work is complemented with quantum chemistry and X-ray diffraction where appropriate. So certainly in the NMR crystallography field, we don't want to be narrow-minded and not taking advantage of all the tools available. The ideal scenario is we bring in data from different types of experiments to produce the best structural model in agreement with all available data. And I've got 5 examples to go through today to give you some idea of types of materials that we're looking at. Excuse me. So this nonlinear optical material, a zero thermal expansion material, some news on the vaterite polymorph of calcium carbonate, which has been going on in the literature for some time. A little bit on halogen bonded solids, which is a topic that my group has been working on a lot in the past five or so years. And finally, an example of, I think, some of where the real power of solid-state NMR is in characterizing dynamic systems. So briefly, obviously I don't have time. There's no point in going into a whole background on NMR techniques in this talk. But I just wanted to give you a feel for the interactions that we're working with in NMR. So the chemical shift you're probably all familiar with certainly from solution NMR studies. In the solid state, I guess the important thing is each unique chemical shift reports on the number of sites in the crystal structure. So the number of non-equivalent atoms in the unit cell. So for example, the number of carbons in the asymmetric unit will show up in our carbon solid-state NMR spectrum. And there are various advanced methods for honing in actually on the various allowed space groups if you know something about the structure. Dipolar coupling is perhaps the most direct structural measurement you can get from NMR. It's just the direct dipole interaction between spins. and depends on the inverse Q of the distance between spins. So if we can get these dipolar coupling constants, that gives us exact structural information. J coupling between nuclear spins can provide bonding information, whether a single bond, double bond, or across multiple bonds, giving us structural information. And the quadrupolar coupling applies to spins, nuclear spins greater than 1/2, which is about 75% of the elements in the periodic table. And without going into too much detail, I mean, this is a second-rank tensor, just like the chemical shift, which is quite useful reporting on site symmetry. So with these interactions, you can really pin down, what is the site symmetry at a particular nuclear site. And again, use more advanced techniques. You can say something about the space group. And this applies to diamagnetic compounds. There are, of course, paramagnetic compounds where the paramagnetic interaction would also become important, but I won't be talking about any of those today. So just to give you an idea of what we're going to be talking about here with the chemical shifts, we do magic angle spinning, where we pack the sample into a rotor like this and spin it rapidly about the magic angle of 54.74 degrees. And that collapses this broad powder pattern into a series of sharp spikelets here, where you have one center band for each crystallographically unique atom in the crystal. And again, that's kind of one of the big advantages that you can get from this is unique chemical shift for each crystallographically distinct atom and can limit the possible space groups. This is different, of course, from what you get for NMR in solution, where a rapid isotropic tumbling will cause things to average out, and you don't get a separate peak for each crystallographically distinct nucleus because you're in solution. Now, there's this book that came out a few years ago, NMR crystallography, which is worth looking at. And in the introduction, it's stated here from R.K. Harris, one of the simplest definitions of crystallography states merely the study of crystal form and structure. And as alluded to in the introduction, I mean, this has been going on, getting structure from NMR spectra has been going on since the very early days of NMR. So here in 1948, this is from Paik, who was a well-known figure in the field from that time, and getting out from the dipolar coupling in a single crystal of gypsum as a function of angle, you can get the precise distance between the two protons in that structure. And this is, as I say, way back, in the first few years of NMR. In a simple system like that, already you can get structural information. Before getting into my examples, I wanted to give you some idea on how we use the data in structure refinement and or solution. And as you all know, we can use our data either as restraints, where we include all these data in a cost function and the structural model is actively refined against the data, or we can use some of our data as cross-validation, where we exclude these from the cost function and then cross-validate against the test set. And of course, this is well known in X-ray crystallography, and has also been employed actually in protein and nucleic acid NMR. So this is just an example of what we do in solution NMR for the structure of proteins and nucleic acids. These are a series of dipolar coupling constants where you have experimental and predicted values for a given structure. You have a working set and a test set, just as you would have from diffraction data. And we've been working to do these sorts of things in solid-state NMR as well. Another important point I wanted to touch on was the idea of using computation in this field. And by computation, I mean typically density functional theory computations. And it's important to touch on this because a lot of the methods, the NMR crystallography methods, as I say, they don't rely purely on NMR data. They would rely on some combination, usually of diffraction, NMR data, but also DFT computation. And this is because there's no simple one-to-one relationship, for example, between a chemical shift and a very precise feature of the crystal. Chemical shifts, as we know from proton and carbon NMR, they're somewhat empirical. I mean, they're not empirical, but there's no easy one-to-one correspondence between between a particular environment and the chemical shift that you can easily get at. So we use DFT, but you have to really be careful because to get accurate results, this depends on a huge number of factors. Okay, so obviously the choice of computational methods, so if you're using DFT, what functional are you using? What method are you using? What about rotational vibrational effects? Obviously, where are your hydrogen atoms? You know, this is going to be very important if you're looking at things where you have hydrogens. Basis sets, if you're looking at heavy atoms, you need to worry about what pseudopotentials you're using. If you're looking at heavy atoms, you need to worry about relativistic effects. Is the geometry optimum? What about solvent effects, other temperature pressure effects? And then periodic versus cluster calculations is a big thing these days. So you can run a calculation on a given molecule to get a chemical shift. But nowadays, the big thing is to do these so-called GPOD DFT calculations where you model the infinite crystal lattice. And this has a huge effect on the calculated NMR parameters. And so the point I want to make here is there's a lot of things to consider when trying to assess how good your computations are or your structure are one versus the other. Okay, there's a lot of things to take into account. You don't not necessarily going to expect perfect agreement. I wanted to make a note on quadrupolar nuclei and NMR crystallography. So as I said, the vast majority of NMR active nuclei in materials chemistry are quadrupolar, so a nuclear spin greater than 1/2. And so there's a lot of examples of NMR crystallography in the literature, which I'm not going to be talking about today because it's not my own research, but for solving, for example, structures of zeolites and small organic molecules, these are all made up of, or a lot of these systems are made up of spin 1/2 nuclei, where there are kind of some established methods. But work in my lab, we do a lot of things on quadrupolar nuclei, and the spectra of these quadrupolar nuclei can be a lot more complicated, a lot broader. There's additional interactions, but if we can get at that information, there's a lot of potential there to relate that to crystal structure. And so most of the examples I'll be showing you today from my group are looking at these quadrupolar nuclei. Okay, so leading into my first example of how we first refined a couple of structures using a kind of combined NMR X-ray DFT approach. You know, you could say first there's a structure solution step where you take information from powder XRD, chemical intuition, and solid state NMR, and you can solve a structural model using some, for example, the Fox software. You can then, as opposed to a solution, you can do refinement. So starting out with, say, accurate unit cell dimensions, and then a DFT refinement to give you some starting point, we can then move on to really using the NMR data to improve on DFT-based coordinates using experiment, and then we can cross-validate this model also using additional data. So that's what my student Fred here did in this first study. And really what we wanted to do here was take the idea of, in this case, using a DFT optimized structure, because DFT structures can be quite good these days. And we thought, well, we can get a DFT optimized structure. Already we're getting pretty close. What if we took our NMR data and we took our structural model and basically forced the structure to perfectly reproduce the NMR data? Okay, so obviously that's not going to be an ideal thing because the NMR data has some inherent error. The NMR data do not completely determine the structure. Okay, it's an underdetermined problem in this case using electric field gradient tensors. So what we wanted to do is make use of both the experimental quadrupolar coupling parameters and the DFT energy in this cost function where we have a relative weighting between the two terms, where we don't want to overweight one or the other. We don't want to force it just to the DFT structure, but we want to weight things appropriately. So this is what we did. So initially we set this up on aluminum oxide, where we kind of optimized the weighting between how much we wanted to weight the DFT structure, the DFT component versus the NMR data. And obviously, if you weight it purely on NMR data, you're going to get a perfect fit to the NMR data, but then if you compare it to a reference structure, the coordinates are off because you've overfitted the data. You could then fit it purely to a DFT structure, and you'd get a perfect fit to the DFT energy, but then now your NMR data don't match quite as well. So we went through a process to find kind of the optimum balancing between the NMR and the DFT. And then we applied it first to this nonlinear optical material containing actually all quadrupolar nuclei, so sodium, aluminum, boron, and oxygen. And so what we did here is first, I have some plots here for all the quadrupolar nuclei in this system, so boron 11, oxygen 17, sodium 23, and aluminum 27. And what these graphs here are, they show some experimental quadrupolar coupling data for these nuclei, not from this compound, but for simple structures where the data are known very well from single crystal NMR. And so where we expect the data to be highly reliable, and we computed what we expect to get from their crystal structures, which are also taken to be highly reliable, so typically neutron diffraction structures, to give us a correlation showing us how well can we expect our computations to reproduce the quadrupolar data if we have a really high quality structure. So this is what you see here. So, you know, depending on the nucleus, the slope is not the same, the correlation is not perfect. But this kind of allows us to calibrate our computational methods now to go look at a different system. And so we're able to measure the NMR spectra for all isotopes in this system. So there's some sodium NMR data, the O17, the boron. And what we did here was just try a few different methods for seeing how we could improve the structure. So starting either from a powder X-ray structure, for example, and then using this weighted process where we iteratively refine the structure against the quadrupolar coupling data and also using a partial DFT weighting to arrive at a final structure, basically, which was in better agreement with all data. So the RMSD relative to the single crystal structure was better. The cost function obviously went down. These are by quite small amounts in this case because it's obviously they're all heavy atoms in this structure. But what really convinced us that we were doing the right thing is that we used the chemical shifts then, which we did not include in the structure refinement process, to cross-validate what we were getting. So you can see the chi-squared based on the chemical shifts for these data drops quite a bit by incorporating this combined process where, in this case, we started with a powder X-ray structure and then included this weighted quadrupolar coupling and DFT data. We then next went on to apply this similar method to this near zero thermal expansion material with some collaborators at Dalhousie University. Okay, so this is an interesting compound that they were working on, which, as you can see over this range, hardly expands. And they were interested in getting the structure because they were having trouble getting single crystal data, so they saw our paper and they came to us. And so again, my student Fred followed up on his method. Started with the Fox software to come up with an initial structural model. We had the unit cell dimensions and potential space groups from powder X-ray. So it came up with an initial structural model as described here. And then we did the same thing as before, so we calibrated our computations for each of the isotopes in this material. So again, all quadrupolar nuclei. And you can see that this DFT approach reliably predicts the quadrupolar tensor parameters for all atoms in this compound. And so we refined the structure the same way as we did before. I'll just show you some of the NMR data. So we're able to get data for all these nuclei. So magnesium 25, zirconium 91, molybdenum 95. A lot of these isotopes require very high applied magnetic fields for sensitivity reasons and to narrow the spectra. But you can get a lot of information, for example, on the number of crystallographic sites directly from the spectra, which helps pin down space group and that sort of thing. So for example, here in the oxygen 17 magic angle spinning NMR, if we go to very high field, this is a 900 megahertz spectrometer, we can actually deconvolute the exact number of oxygen sites in the compound. And this was key in supporting the structural model and space group that we came up with, which actually had the correct number of crystallographically distinct oxygens. And so interestingly, the refined structure in the end agrees remarkably well with the experimental quadrupolar coupling parameters. The NMR DFT refined structure better reproduces the 017 NMR data, which were used as cross-validators. So in this case, the 017 data, as I say, was used as cross-validation. So if you look on the left here, these are quadrupolar coupling data. So you can see, for example, this line here would be a perfect fit. And you can see the initial starting structure, reed field structure in green. We have points that are way off the line. Even if we look back here, it looks pretty good by eye, right? But these quadrupolar coupling constants are very, very sensitive to small local changes. And so if you zoom in, you can see that there's a lot of points that really get improved by including the NMR data, and things end up being in much better agreement. So in the end, by using this type of approach, not only are we in agreement with the powder X-ray data, but now we have this kind of fine-tuning of the local positions of the oxygen atoms as well. And so they were able to use this structure to help infer something about the mechanism of their near-zero thermal expansion material. We found the structure was very similar to the scandium version, albeit with a lower symmetry. The molybdate tetrahedra are connected by MgO6 or ZrO6 octahedra. And as I say, they were able to use this to explain what was going on. Okay, I wanted to say something about vaterite, which is a metastable polymorph of calcium carbonate, which you may all know about. And we wanted to assess various structural models in the literature via calcium-43 solid-state NMR. So there are three anhydrous polymorphs, calcite, aragonite, and vaterite. And there's been a lot of papers about this in the past 10, 20 years. We've done some NMR work looking at calcite and aragonite. And given the distinct symmetries of these compounds, the calcium NMR is very useful in reporting on the local symmetry, for example, at the calcium. With vaterite, there's been a whole lot of different structures or proposed structures in the literature. We first looked at this story in 2008, and there was a series of kind of possible contenders. So initially, we reached one conclusion about this P6-3-MMC structure, but there's been a lot more work since then, a lot of new developments, so there's kind of new models coming out almost all the time here. So hexagonal structures in space groups have been reported. There's been a proposition of a mixed phase structure for vaterite, so one major phase and another minor structure that was reported in Science. And then also some proposed monoclinic structures recently. And I liked in their paper here, they claim that NMR is not suitable for distinguishing the correct model. Okay, so that made me want to follow up on this further and see what we could do. And this is a picture from someone else's paper here that I thought kind of nicely summarized some of the situation. And they did some DFT computations to try to look at the series here, so hexagonal, monoclinic, and look at the relative stabilities of these phases to get an idea of which one might be the true lowest form. But the point I'm trying to make is simply there's a lot of different possibilities out there, and I'll show you what we've been able to do. So my student, Kevin Burgess here, we kind of, in 2015, summarized what we thought were the kind of the major players reported in the literature on the structure of vaterite, so the hexagonal, monoclinic, and orthorhombic structures. So there's some experimental structures here, there's some DFT structures, so some are just proposed. And what we want to do is simply evaluate each of these structures against powder X-ray and the calcium solid-state NMR to see which ones could easily be ruled out, for example. And so right away, by looking at the powder X-ray diffractograms, there's a few that were quite easy to rule out. Importantly, when we prepared our vaterite sample, we made sure to check it a few months later, because one of the questions I always get, well, isn't vaterite a metastable polymorph? So, you know, it won't be changing if you do your experiments a few months later. But it has the same pattern 2 months later. So the point of this slide here is that, yeah, there's a few you can rule out right away by looking at these diffractograms, but then there's a whole bunch that right away you see, well, there's a lot of similarities here. We're going to need to look further in depth. And so we wanted to look at the calcium-43 solid-state NMR. And what you have here on the left is an experimental spectrum and then a simulation above it. So under magic angle spinning at 9.4 Tesla, at 21.1 Tesla, and then a static powder at 21.1 Tesla. And by simulating these patterns, we can get out information on the quadrupolar coupling parameters and chemical shifts. And then some more advanced experiments on the right here. This is a multiple quantum magic angle spinning experiment. And what this does is separates the effects of the chemical shift essentially from the quadrupolar interaction. So it pulls apart into 2 dimensions to, typically the experiment is used to reveal multiple sites that you're not seeing in the one-dimensional spectrum. And basically what we see here is there's still only one site. At the top here, this is a double rotation NMR experiment, so another kind of fancy experiment to try to tease out whether there's more than one crystallographic site. This double rotation experiment is you have a rotor placed inside another rotor. So you have one rotor spinning inside another rotor, all inside the NMR probe. And so your sample is simultaneously rotating about 2 axes at the same time to give you the averaging required to get isotropic resolution. And so what you see here is this kind of noisy peak for the vaterite, but it pretty much looks like it's one thing. There's not 2 peaks there. In the top right there, though, this is a crystalline calcium sample, calcium nitrate. And you can see how sharp that peak is on the same chemical shift scale. And so what this tells us is that in vaterite, yes, it looks like there's one calcium site, but there's definitely a lot of disorder around that calcium because this broadening of the peak compared to what we get in a crystalline sample is huge. So single crystallographic site, but definitely evidence of some sort of disorder. This is kind of a sideline, a point along the way. There was various improvements since we first got into this project on how to interpret the calcium NMR data. So I won't go through all this, but it comes back to calibrating our computational methods to be able to get the right answer. And we were able to calibrate a lot of calcium NMR data on, again, crystalline compounds with high-quality structures to get a new quadrupole moment for calcium-43. And this is basically what we need to then take DFT values, translate them into something we can compare with experiment to test our models. So one of the things we can do is plot our experimental spectrum for vaterite and then overlay some simulations based on what we get from DFT computations. Okay, so in red is the simulation, which just kind of best fits the experiment. And then here's a bunch of the proposed structures. Okay, so on this slide at least, this P65 and C1 seem to be in okay agreement. These ones are not. Okay, so major structure is this or this, minor structure is this. This was inconsistent with the people who said that NMR couldn't tell the difference, but consistent with the work that was published in Science that proposed the interspersed structures. So this is a lot more of the same thing. Basically, what we do is we look at our experimental spectra and then generate the simulated spectra for all possible proposed models and see what fits and what doesn't fit. And you can do this in a qualitative way just by looking at it, or we can quantify the differences, which we did. So for some of the top models here, you can see, so for the quadrupolar coupling constants and the chemical shifts, what we have here are, for a series of models, kind of what we get with an experimental error. And you can see there doesn't seem to be one model which fits perfectly, and this is consistent with the idea that there's perhaps 2 structures that are interspersed. But nevertheless, there are a couple of models, for example, this P321, which do agree well for chemical shifts. And so the conclusions here are some models are completely inconsistent with the powder X-ray data. we found that the P321 model and the monoclinic C-tube model provide the best simultaneous agreement between the experimental and calculated NMR data and the experimental and simulated powder X-ray data. But interestingly, none of the 18 structures provide perfect agreement between experimental and simulated data within the established RMSD values for the various NMR parameters. And again, I don't think this is surprising given the complexity that seems to be coming out in some of these recent papers that talk about an interspersed structure. So what we're doing now is following up with oxygen-17 NMR because presumably there's a lot of disorder arising from the orientations of the carbonates. And I had to show this because this came out just quite recently. There was a review of the structures of vaterite, the impossible, the possible, and the likely. And when I saw the title, I thought, oh, I hope ours is one of the good ones. And so I was happy to see that it was. So in the consensus, the structures that fit most of the ab initio modeling, diffraction, and Raman data are the 2M polytype with symmetry reduced to C121 due to small carbonate rotations of the type shown here, and the 6H structure with symmetry analogous reduced to P321. These structures are also the most favored by a recent calcium-43 study of vaterite. So I hope that that's an independent, unbiased assessment that what we're doing seems to work. So in this little section, I've shown you how we can use the NMR data as restraints or cross-validators. Quadrupolar nuclei pose challenges but offer a wealth of structural information. And okay, I've talked about those three examples. I've got two examples left, or two small sections left. So we've been doing a lot of work on halogen bonds. I don't have time to go into all of that today. I just wanted to give one or two examples. Some of you may be aware of all the work that's been going on in this area. And the halogen bond, as you may know, is created by a depleted electrostatic potential opposite a bond here where you have electron withdrawing capacity on one side. So for example, in CF3I, you see this polar flattening or sigma hole on the far end. And so the iodine, or the bromine in this case, then can act as an electron acceptor. And there's been a lot of work in this area. So a book on halogen bonding, there's a good review here on halogen bonds in biochemistry. And these are useful interactions because their strength is comparable to hydrogen, to that of a hydrogen bond, but they're highly directional. They're linear, and so they can be tailored for uses in crystal engineering. And so in this IUPAC definition, again from Desraju, the XY halogen bond usually affects the nuclear magnetic resonance observables, e.g. chemical shift values of nuclei in both Rx and Y, in both solution and in the solid state. And so here's a typical halogen bonded fragment where you have some sort of electron source donating electrons to the sigma hole. And so we're interested in seeing what can we learn about halogen bonds in solids. And so consider the information NMR provides on hydrogen bonds. I mean, this is a big deal, big strength of NMR, certainly in solution, but also in the solid state. So for example, here, if you look at the hydrogen bond in proteins, you can get, from J couplings, direct measurement of distances. So stronger hydrogen bonds give higher chemical shifts, stronger hydrogen bonds give larger J couplings, so these are parameters that we can use both in solution and in the solid state to tell us something about structure. So we were interested in seeing what we could do with halogen bonds. We've published a lot of work in the past few years, but I'll just give a couple examples here. So in this compound here, we've got a bromide ion donating electrons into this para-diiodotetrafluorobenzene molecule. It's actually two different ones. And we're interested in looking at the carbon chemical shifts of this ipsocarbon to see how do they correlate with the strength of the halogen bond. These are actually quite difficult to get due to long relaxation times and relativistic effects due to the iodine. But nevertheless, we were able to get this nice correlation between that chemical shift and distance. Okay, so somewhat analogous to what you would get for a hydrogen bond. So we can put that in the same framework of what we have for hydrogen bonds. So here we have carbon-13 chemical shifts in this fragment in proteins, and 15 chemical shifts for this fragment in proteins, and now here what we found in halogen bonds. And so it's kind of an analogous situation. And again, this applies in solution and in the solid state. So in all cases, as written at the bottom here, the chemical shifts of the groups bound to the electron acceptor and the electron donor increase as the non-covalent interaction strengthens. So this might not give us, obviously, direct crystallographic structural information, but I think one of the things that's important to keep in mind is all of these solid-state NMR methods are widely applicable for heterogeneous samples where you don't have high crystallinity or things don't crystallize well. You're still able to get your spectra and get this information. Okay, so one little example here of recent work we published in a special issue on NMR crystallography in ActorCrysC, looking at the CI-N halogen bond, which is relatively unexplored by solid-state NMR. And so we did a series of co-crystallizations using these iconic halogen bond donors and a series of nitrogen-containing acceptors. Oops. Okay, and we're able to get out a nice series of structures here. We have some bifurcated halogen bonds. So these structures are all from diffraction. So some bifurcated halogen bonds, some single halogen bonds, and some very nice structures, which one of the things that we're trying to do here is if we're setting out to look at the CI-N halogen bond by solid-state NMR, we're going to start with systems where we know the answer, right? We're going to start with systems where we have the so-called correct answer from established X-ray crystallographic studies. So that's what we're doing here. We have the structures from X-ray. In these particular structures, you can see the strength of the halogen bond is down to about 80% of the sum of the van der Waals radii. This work was done by my student Pat. This is just kind of a zoomed-in version of the compounds showing a different perspective on the halogen bonds. This is the view of the crystal packing. They form quite nice networks in the solid state, and these are established by not only the halogen bonds, but some CIF close contacts. And so now we know the structures, we know what they look like. We want to get the NMR spectra to try to make some sense of what it can tell us in terms of halogen bonding. I'm not going to walk through all these spectra, but these are carbon-13 spectra of all those compounds, and obviously you can assign all the peaks to various chemical shifts. We were able to look at fluorine to carbon cross-polarization, solid-state NMR. Look at the fluorine NMR, and unsurprisingly, there's a shift associated with the presence of the halogen bond. So clearly identifiable changes in the fluorine-19 chemical shifts upon halogen bonding on the order of 5 to 15 ppm. So this shift as a result of halogen bonding or co-crystallization is kind of a nice, pretty clear-cut indication that you have co-crystallization as opposed to just if you had the two compounds mixed physically as powders. But this experiment is that I'm showing you here is more clear-cut proof of that. So this fluorine to carbon-13 CPMAS experiment, we're taking magnetization from the fluorine atoms and transferring it to the carbon atoms and acquiring our spectrum. And so what you can see for this co-crystal here is if these were not halogen bonded, if they weren't co-crystallized together, we would not, for example, expect to see any methyl peak in this spectrum, right? Because the methyls are only on this moiety. Okay, but we're taking magnetization from the fluorines, transferring it to these carbons. In order for that to work, they have to be basically halogen bonded to each other. If they're further away in the crystal lattice, or if they were just physically mixed, you wouldn't see this in the spectrum. Now, this is kind of an example where we use the powder X-ray structure with DFT, so a DFT optimized structure to get an improved structure. So if we take the powder X-ray structure and the single crystal X-ray structure, and we calculate the carbon chemical shifts, and we put them on a scale and see how well they correlate, this is what we get. If we do a DFT optimization of that same experimental single crystal X-ray structure, you can see how much better things get. I should point out that these orange points are for those carbons that are directly bonded to iodine, where the relativistic effects are very difficult to capture properly. This is the same type of thing with the fluorine NMR results. So based on the single crystal structure and then after DFT optimization. So this is an example of, I mean, it's a diffraction-based structure for sure, but by taking the X-ray diffraction, doing a DFT optimization, we then are essentially using the NMR data as a cross-validation to show that the final structure that we've got is in a little bit better agreement with the NMR data. So this is kind of using NMR to select the best data as opposed to structure as opposed to actively refining against it. Okay, so in the final section, I want to tell you about some interesting new experiments that we developed to probe crystallographic symmetry and dynamics. I won't go through this complicated pulse sequence, but it's a spin echo sequence to measure J couplings between pairs of quadrupolar nuclei. Okay, so in this dimanganese decacarbonyl, we were able to measure the J coupling between those manganese atoms. And interestingly, in this experiment, what we found is that the splitting that you get in the NMR spectrum is actually amplified depending on the spin quantum number. So if you think of solution NMR, the protons on a methyl group, if you look in the NMR spectrum, you don't see the coupling between those protons because they're magnetically equivalent. It doesn't mean the coupling is zero, it just means that you don't see it in the spectrum. And so here you can see that in this experiment, the splitting is amplified by 0, which makes sense. There should be no splitting for spin half nuclei. But for these higher spin nuclei, you actually get an amplification of the J splitting, which was kind of an interesting finding. Okay, so in this experiment, and this only happens if they're magnetically equivalent. Okay, what does it mean if they're magnetically equivalent? It means basically they have to be related by an inversion center or some other, there's another subset of very high combinations of very high symmetry operations that will render them magnetically equivalent. Okay, so not just crystallographically equivalent, but typically related by an inversion center. And so if they are magnetically equivalent, we get this amplified splitting. If they're not magnetically equivalent, we don't get the amplified splitting. And it's a very nice experiment in that it's unambiguous as to what is going on with the symmetry in the crystal. So I'll show you some examples. So if you look at this compound here, in this compound, the crystal structure shows that the borons are magnetically equivalent. We broke the symmetry of this compound by coordination with this N-heterocyclic carbene. And then I'll show you the results here. So this is the starting compound. There's the splitting, the amplified splitting of 3 times the J coupling constant. This is just another reference compound to show you that it works for other compounds too, where there's crystallographic symmetry. You get a slightly different J coupling because it's a slightly different compound. But then when we break the symmetry, you can see it collapses to a splitting of just J. So this is a very direct, unambiguous indication of whether you have magnetic equivalence between the spins you're looking at, so basically inversion symmetry relating them. And we can relate the J couplings in these compounds to the boron-boron distance, for example. So here's an example. We've tested this out on many compounds where we have high-quality diffraction structures, where we know in advance are the borons related by an inversion center, are they magnetically equivalent or not. And in all cases, this agrees with what we get from experiments, so a splitting of J or 3J. So you can see, for example, let's see, so compound 6, even though in this ChemDraw representation, the borons would appear to be equivalent, well, the splitting is only J, and in fact, in the crystal structure, they're not related by an inversion center. So this is really, I think, a quite useful, clear-cut application that gives us very specific information. So now, the next part of this is we wanted to see if we could detect dynamics using this experiment. Okay, so I already mentioned the idea of 3 protons on a methyl group. So what if our magnetic equivalence arises from motional averaging? Okay, so what if we had 2 borons that were moving around that, in fact, they're moving so fast isotropically that they appeared to be magnetically equivalent? And so that's what we looked at with these collaborators. They prepared a series of these compounds here where we've got the hexacyanodeborane 6-dianion, so 2 borons with 3 cyanos on each side. And they got X-ray diffraction structures for these, and you can see they got a range of behaviors. So this one was quite well behaved, and then we had disorder in several others. And it wasn't clear whether it was static or dynamic disorder. And so we wanted to apply our experiment to look at these compounds to say, well, you know, if the relationship between the boron atoms suggests that if there's static disorder, that the borons are still magnetically non-equivalent, we would expect a splitting of J. But if instead this is really dynamic disorder, we would expect to see the amplified splitting. And so we wanted to investigate dynamics. So first thing we can do, let's look at 2 compounds here. We recorded the carbon-13 solid-state NMR spectra. So if you look at these structures and all the possible you know, sites, disordered sites, there's up to 60 inequivalent carbon atoms in this crystal structure, 44 in this one. Okay, now I told you at the beginning with chemical shifts, we expect 1 peak for every distinct carbon atom in a crystal structure. If you look at these spectra, even allowing for fortuitous overlap, there's no way there are near 60 carbons in that spectrum. Okay, so already this is a sign that there's dynamic averaging, and this is not static disorder, but dynamic disorder. Same thing from looking at the boron-11 solid-state NMR experiment. If these were statically disordered, we'd expect 8 inequivalent borons, okay? Even allowing for overlap, it doesn't look like there are 8. We did some variable temperature carbon-13 experiments on the cyanocarbons. So those are shown here for compounds 4 and 5. And if you lower the temperature here all the way down to 173 Kelvin, it broadens out to what you would expect for a static nitrile carbon. Okay, so for known systems where we have a static system, that carbon spectrum should span 320 to 350 ppm, but in this case it spans only about 30 to 60 ppm, so another huge indication of dynamic averaging. And so we were able to fit that using a model here. So we actually had to take into account 3 different motions to do this. So these 3 models, A, B, and C, one of them alone could not account for this motional averaging. And any pair of them could not account for it, but all 3 of them together did. Excuse me. So the first motion we considered was simply rotations like an ethyl group. So we have this B2CN6, and we just have ethyl group type rotations. That was one of the motions. And then the other 2 motions are basically, I had 2 little movies here, but they're basically showing the compound hopping back and forth between the various crystallographically allowed sites in those models. And so by putting those 3 motions together, we're able to reproduce the data. And these have correlation times ranging from 10 to the 2 to the 10 to the 6 per second over the temperature range 248 to 306 Kelvin. And we get all that by fitting this as a function of temperature. Okay, so then in the end, when we look at the splittings for these, they all turn out to be 3J, even though we would have expected in these cases here, 4 and 5, that if there was no dynamic averaging, we would not expect to see the amplified splitting. So taken together, all of these results are clear indications of dynamics in these systems, and our experiments are kind of a new and sensitive probe of dynamic disorder, and we can use these then for detecting molecular dynamics. Finally, we can correlate these coupling constants with the structures of the compounds. We've been looking at a lot of boron-boron couplings, both in boron-boron single, double, and triple bonds, and a range of systems, and everything correlates nicely over the whole range in terms of looking at hybridization of the boron and the bonding energy, et cetera. So the conclusions on this last section, these two-dimensional J-resolved solid-state NMR experiments provide J couplings between pairs of quadrupolar nuclei. The observed splittings report directly on magnetic equivalence and therefore crystallographic symmetry. So it's very clear-cut, for example, whether there's an inversion center or not. And under favorable conditions, we can use the observed J splittings to provide a novel probe of molecular dynamics. I think that brings me almost to the end of my talk. I didn't prepare a large conclusion slide because I've kind of summarized as I went along. So I'll just point out that a lot of the work that we do relies on making use of very high magnetic fields because these quadrupolar nuclei really rely on the high fields for line narrowing and for sensitivity issues. And so a lot of this work relies on the 900 megahertz spectrometer that we have at the University of Ottawa. And I didn't list everyone's name, but certainly I want to acknowledge all the people who contributed to this work, and my current group, and the various funding agencies. And I think that's all I have to say, and I thank you for your attention.
Thank you for that wonderful presentation. We have time for just a couple of quick questions. There are microphones available if you would find your way.
Yeah, thanks for that wonderful talk. To my impression, solid state and solution NMR starts to amalgamate, right? We use ordering media swollen gels to identify the shape of molecules. Could we do the same with crystal sponges known from Fujita's work? Could we dip just the crystals in and then run an NMR and find out what's going on? What's your vision?
Find out what's going on in what sense?
How to identify chirality inside cavities. Find out what the size of the molecules is sitting in that cavities. Find out what the aggregation is.
I mean, anytime you...
Will the molecule, say, shift out, kick out some solvent?
I mean, if you can introduce some partial ordering to the system, then yes, all of a sudden you're able to kind of weight the various NMR interactions exactly how you want them to tease out the information you want. I'm not sure the crystal sponge method itself, I'm not sure what advantages it would have for NMR. But certainly, for example, in the field of biomolecular NMR, the use of alignment media has been a huge advance for teasing out extra information.
Two quick technical questions. What is the pressure in the probe? I mean, you start spinning up to 130 kilohertz, right?
Yeah.
And the pressure is considerably high.
Yeah.
Can you verify, can you guarantee that the structure remains the same while this rotor is stuffed and then spin?
That's a great question.
Yes,
would you like to go first?
So the pressure is actually very low because you don't have much mass inside. So you have very high G values, but you have practically no pressure. It's around 1 bar. So.
All right. Thank you.
But certainly there are cases where you can monitor changes happening inside the rotor as a result of the spinning.
Good.
It's not typical, and you can obviously verify that by comparing spectra at the beginning and end of your experiment, but it's something to be aware of, and we've seen examples of that.
Good. Last technical question, sorry for that. Would the dual rotation method require a special probe?
Yes, and nobody makes them anymore.
I'm not asking what it is like in costs. So.
Yeah, you can't buy them anymore, I don't think.
You can't, you make them yourself?
Well, we ended up getting an old one from Brooker that they had lying around. But,
this is why you abused the logo, no?
As my students.
Thank you, David, for a really lovely talk. A comment and a question, if I may. The comment, I note that you've done plenty of powder X-ray diffraction, but you don't indicate you've done powder neutron diffraction, which has the advantage of the pattern extending way out in theta because you don't have the fall off in the structure factor with angle. So that might be a source of further data for many of your comparison experiments and give you greater leverage on your problems. My colleagues at ANSTO and I think at other places have mail-in services for powder X-ray, powder neutron diffraction available now, which might be very useful to use these techniques in tandem. My question is, do you have the opportunity in that last example to do 2D cross-polarization experiments which have previously been shown to be very effective at fishing out the dynamics in systems?
So like an exchange experiment?
Yeah, 2D carbon-13 side exchange experiments.
Yeah, I mean, we didn't do those experiments on this particular case. We were sure they could be done. Obviously, there are many ways you can get at dynamics from NMR. In this particular example, we were interested in seeing what we could do with this amplified J-splitting.
Yeah, of course, it would be an additional method.
Yeah.
And it has in the past been used to good effect.
Yeah. Thank you.
Thank you.
Thank you.
Maybe time for one last question. We're nearing time.
So I have a short question about the estimation of the quadrupolar coupling constants. So we are working on MOFs and zeolites a lot with aluminium NMR. And there the experience is that the quadrupolar coupling constants are always a little bit overestimated. How is it in your case?
Yeah, so that's, I believe that's what we had for everything that I showed here. The slope of the correlation was around 1.1. But you know, this is something to be really aware of, because in the literature, as I'm sure you're aware, there's a lot of some over-reliance sometimes on people expecting the calculations to be exactly right, and for many reasons, you can't always be sure that that's the case. But yes, they do, not always, but in the cases that I showed, they also came out higher. That's why we calibrated them in the case of our refinement example.
Let me encourage you to bring your curiosity and your questions to the Microsymposium number 24 tomorrow morning, where we will feature 6 speakers in the field of NMR crystallography who will speak to some of the issues that David Bryce raised early on in the different facets of NMR crystallography. So that will be happening tomorrow morning. And to close our keynote, I'd like to invite a member of the local organizing committee to close us out.
So on behalf of local organizing committee, I am, it's my pleasant duty to give small gift to the speaker and small gift to our chair.
Thank you. Thank you very much.